The plan is we'll hit the lesson, go over what the test will cover, and then we'll get questions on the homework, and we'll all be happy. Are you ready? Yes. Now, you learned the power rule the other day, and that is a super handy shortcut. But not everything is x to a power, so you also need to know how to take the derivative if you see e to the x, or natural log, or sine, or cosine. That's today. Now, when you introduce derivatives, you usually do it one of two ways. You either do it in the definition or graph. The definition for these is pretty gross, so we're going to do this graph. That's the idea of all those graphs on the front of that. I will do one with you together to communicate how to do this, and then you will do the other three. First of all, let me communicate the goal. The goal is to figure out the derivative of sine graphically. We're going to do that by remembering that the derivative means tangent slopes. At each point, you should have an exact slope. And so if you just find the slope at an interesting point and record it on a graph, then you start to get a picture of the derivative, and hopefully it looks familiar. So that's what we're going to do in this space right now. So let's start at 0. If I were to draw a tangent line here, what does that f prime, the derivative at 0, look like? Slope-wise, just ballpark. I mean, we might not all agree, but ballpark. Come on, okay, I agree. Now, you're going to graph the derivative, or record those values down here. At 0, we say the slope is 1. So once you get an estimate, you're first going to estimate, then you're going to record it here. How about at this point? Now looking at the scale, I'm going by ones, but what really is that maximum at? Where's sine at a max? Where's the top of a wave for a sine curve? Pi over 2. What's pi about? Yeah, 3.14 over 2, that's about 1.57. So do you see where that peak is coming from? It's between 1 and 2 because it's about a pi over 2, yeah? What does the slope look like there? F prime at pi over 2 looks like 0. So if you locate that same point here, pi over 2 again would be between y or 1 and 2. If the slope is 0, then the derivative is 0. How about at the next point? What is this point I'm showing here? Exactly. It looks pi. F prime at pi. Estimate that slope. And again, that's an eyeballer. We don't have to agree. Ballpark? -1. At pi, which is a little past 3, -1. And how about over here at, which really amounts to 3 pi over 2, or 4 halves-ish. What's the slope there? 0. Now I could continue to go backwards here. For example, at negative pi over 2, what's the slope there? 0. At negative pi, what's the slope there? Looks like about -1. And at negative 3 pi over 2 there, that's about 0 again, yeah? If you draw a smooth curve then to look at the trend of the derivative, it appears that the derivative of sine is cosine. The derivative of sine is cosine. Now, with that idea, go over to the next one. Quick explanation fact though. If I do the natural log of plain old x, then you can't take the log of negatives, it's just this side of the curve, right? If I wanted to create or allow for negatives, I could use absolute value. Though you often do that in calculus, especially today, to see the trend. I'm putting absolute value on there so that negatives can be allowed, and you'll see that negatives behave just like positive x's. So that's why the graph has 2 log branches, but the idea is the same. At each of these points, would you eyeball the slope? And I do mean eyeball. Just estimate the slope and record it below at each point. Feel free to talk it over, and we'll go over it in a minute. Do work together. Thank you. In the last class, I tuned out and then they weren't really with me, so if you're not quite with me, what's going on, let me know, I'll be happy to clarify. I don't know anything. Aren't you recording as you go? Let's go negative 1/3. Yeah. Record it. At 3, the y is negative 1/3. Oh, yeah. Put it up. So your recording is still there. Without negative 1/2. At 2, so at negative 2. There we go. Let me know if you need clarification. Okay, I'm seeing a whole lot of blanks, and apparently you don't have the guts to say, hey, I don't get it. I suggest you grow up before college. Here's the deal. If you estimate this, that slope, ballpark looks to be maybe down 1 over 1, 2, 3. That slope then is down 1 over 3 is negative 1/3. Once you get your estimate, you record it at the exact same x. So at negative 3, you go down and record it. Negative 1/3 is here. Then you go to negative 2. You draw another tangent line. You ballpark estimate. Maybe down 1 over 2 now? At that same point, go down here and say the slope looks like down 1 over 2 or negative 1/2. Draw the slope here. That time it looks like about negative 1. Okay, at that same point, record negative 1. There's a point here. The slope is steeper. Give me an estimate of the slope. Negative 2, down 2 over 1. It's pretty steep, so at that point, it's negative 2. Draw a smooth curve. Now do it on this side. Draw a sketch, estimate the number, record it. Draw a sketch, estimate the number of that slope, record it. Connect the dots. Are those slopes on the right or left positive or negative? Oh, sorry, on the right, are they positive or negative? Positive. So, for example, at 1/2, it's looking like 2. At positive 1, it's looking more like 1. What'd you say at positive 2? 1/2. What'd you say at positive 3? 1/3. So it looks like this. So, the derivative of natural log looks like that. This is the derivative graph. What does that look like? 1 over x. The derivative of natural log is actually 1 over x. Okay, that's the idea. Draw slopes, estimate the number, record the number. Try the next two. Okay, conclusions then. Derivative of cosine, it would be logical to say, well, the derivative of sine is cosine, so the derivative of cosine is sine. But is that the case? No, the derivative of cosine looks like this, and that's not sine, that's negative sine. So when you take the derivative of cosine, you're going to get a negative. It's a negative sine, because that's what the slopes say. What about this? This just kooks me out. If I look at those slopes and record them, I get a graph that looks just like the one over there. Well, if this is e to the x, then its derivative is e to the x is the only function in all functions that is its own derivative. Pretty cool. And just one more attribute of e that's amazing. All right, pause for a quick side note. This I'm going to make a quick change to. Let me explain y equals sine of x. I know about calculus and trigonometry, particularly with measurements. Say I were graphing the curve y equals sine, but this time, instead of radians like we did on the front, I did it in degrees. Okay? Sine, I know at 0 is here. Yeah? In degrees, when does sine reach its peak? 90 degrees, okay? So in terms of my scale here, when would I get that peak? This is 1, 2, 3, 4, 5. When would I hit that peak? Somewhere close to Mrs. LeBlanc's room. You see what I'm saying? Okay. Degrees are such a huge scale that everything's going to be all funky. If I were to only go up this much, by the time I went to Mrs. LeBlanc's room, the slope of this would be practically flat. And that kind of happens when you graph from your calculator in your degrees and you thought it was radians, and it looks like a line instead of an actual wave. That's what it would look like if you were to graph over 10 in degrees. It would be almost linear, and the waves are so stretched and long that you're not even seeing it. Now, if you then did the slope idea, and if I then said, okay, what's the slope at 0? Is that going to go up one box, over one box now? No, it's going to go more like up one box over 90 boxes. The slope is about 1/90. It's microscopic here. The slope isn't 1, it's practically nothing. It's so flat. And you would see that it's still practically nothing, practically nothing, practically nothing. And the graph would not look like a normal cosine curve. It would look, if you were to graph the slopes here, it would look something like that. Now, it is actually a cosine curve, but stretched by up high over 180. I mean, it's squished like that. My point is this. Degrees are so wide, and the scale is so far away from a 1-to-1 scale, that in calculus, if you take the derivative of cosine, it's actually of sine. The derivative of sine is cosine only when you're in radians. The derivative of sine is not cosine if you're in degrees, because the scale is so stretched, the slope's not 1 there. It's tiny. It's not going to give you a cosine value of 1. That's why in calculus, you only do calculus in radians. The scale in degrees is so funky that the slopes and therefore the derivatives aren't the same. All right. So, summarize. You learned 4 new derivatives. The derivative of e is e. Now let me specify. The derivative of e to the x is e to the x. The derivative of e is 0 because e is a constant. Okay? So I should have said e to the x. The derivative of log is 1 over x. The derivative of sine is cosine. And the derivative of cosine is negative sine. With those in mind, would you just do this one practice problem, please? Who? Abby's. Okay, thank you. Okay. Okay, derivative of 2e squared. 2e squared, because e is its own derivative. Is 2e squared a function or a constant? It's a constant. I know e, oh, that's very low. E to the x varies. E to the second doesn't vary. It is a number. And therefore, the derivative of a constant has no rate of change. It doesn't change. Its derivative is 0. Don't fall into the temptation of saying, oh, e is a function. It's only a function if it's a function of x. 2e squared is not a function. 3 sine x, what's its derivative? 3 cosine of x. Obviously, if you left that 0 out, you didn't have to write 0. 7 cosine. Negative 7 sine. Negative natural log's derivative. Negative 1 over x. Now notice I didn't put absolute value on that. That doesn't change the derivative. It just means that instead of getting slopes on both sides, you're only getting slopes on one side, but the derivative is still 1 over x. You're only getting positive sides now, but the shape is still the same. Okay? What about 3 root x, which I might do a rewrite on? That's 3x to the half. Power rule that baby. 3 over 2x to the negative 1/2. I suppose you could write a root x in the denominator. It's fine too, either way. And the derivative of 2 is 0. Okay, you don't have to write that. But. All right. How'd that go? Are you with me? Okay. You'll see those. I mean, that's the softest question of all. Derivative of e to the x. Wow. Your eyes should light up and you should be happy after. Next thing, really fast check to make sure you understand what the test is through. This is on the back of the problem set. I'm at the back. If you want to jot down a few notes, I won't break this, so if you don't write it down, it's fine with me. But the test is through set 22. I will not test you on anything you haven't practiced sufficiently. So this test will cover through last week's material. We finished last week at set 22. So the test will be through 22. I would recommend you look at the notes. I do definitely pull problems from the notes in addition to the problem sets that you worked on. So that's a good starting point. If you just look over your notes, it's a good way to study. The transformations seem to go well. That was last Friday. Set 20 and 21 was the 3 definitions of the derivative. I feel like math is kind of like a sport or an instrument. You don't cram the night before. You practice over a long period of time to get good at something. But that said, you can study a little bit for math. For example, you should commit yourself to memorizing the 3 definitions of the derivative. Yeah? Set 19 was the introduction of the derivative idea. And the big idea is that you're taking the slope between 2 points and getting the points closer and closer together, right? Before that, we did the intermediate value theorem, which seems to be going pretty well. Continuity, those can be difficult. Last class, they stunk. I hope you're better. You should know and study the definition of continuity. The limit must exist, which implies the left hand, right hand are the same. Limits are the same. The point has to exist, and the limit and the point have to be equal. Limits, that's actually a huge thing. I just wrote one little word, limits, but that's so many levels. Do you understand that a limit is the approach, not the at necessarily? Do you understand how to evaluate a limit graphically, analytically, numerically? Do you know what an infinite limit is telling you? Do you know asymptotes and how that connects to a limit? Review your limit notes. The summer review, I also will pull some stuff from the summer review. So hopefully you did that. All right. If you need help, or if you feel like I'm a little iffy on this, then I will be happy to give you more practice at your specific request in 7th hour, after school, or before school. Don't come to me and say, give me some practice for the test. I will say, no, go away. If you say, I'm not very good at continuity, can you help me practice? I will say, sure. Let's practice some continuity. Okay, so don't just say, help. That's not going to cut it. Be specific about what you need to work on. All right? And I will help you. That will be great. I will be here before school tomorrow, no later than 7, probably as early as 6:45 or 6. Actually, don't come before 6:45. I don't want to see you. No offense. Set 25. I have some replacement problems, but I failed to put the key up. So let's start by checking those, and any other problems that you want to ask about, I will be happy to help you with those too. I'll give you a second to get set 25 out, and then we will roll. Isn't it nice to have a normal day, or did you enjoy the long days? Kind of like the long days? Yes. Oh, a good question. How I do stuff as far as, I don't collect homework the day of the test. I have to grade the test. So this homework, set 26, is due Monday. So glad you.
That's a Tuesday.
That's what? Tuesdays, right, Labor Day, sorry. Say, you're not used to that? Did they, no, they collected your test the day of the test?
She would have to test the day before the test.
Oh.
And then, but you have to work after the test too.
Yeah, I also, you won't have an assignment the day of the test either. That's just crazy. That's just me. So, yeah. All right. For this, check your answer. Then, if necessary, we'll go over it. For this bad boy, I got that easiest to find was B is 3. Excellent. And A is pi over 2 minus 3. Congratulations. When I asked that question in the last class, I heard absolutely nobody say the right answers or the wrong answers. Great answer. That said, you might not have got that, but they surely did not understand it. So if you'd like to talk about that, we can. Okay, I'll assume then you're great. And you will definitely see something like that on the test. All right, 14. Now this is conics. We didn't cover conics last week. We covered conics this week. So this, if you're not quite there on this will not be on the test. But the first one, what kind of graph is it? Positive half circle, yeah. If you square both sides and rearrange, you get x squared plus y squared equals 4. So it is a circle, but because y is only the positive root, it's only the top half of that circle. The range is 0 to 2. The next one, parabola, circle, ellipse, or hyperbola, which are the 4 conics. Hyperbola, true again. Y squared equals x squared minus 4. I like that constant to be positive, so I'm going to move it over here, and something like that. Sideways opening or vertically opening hyperbola? Sideways, top half, bottom half, or both? Top half. Okay, last one. What'd you say? It is an ellipse. If you rearrange, you get something like 2x squared plus y squared equals 9. Now, in my mind, I think, well, that's kind of like a circle because it's square plus square, but multiplying causes a stretch. So it's a circle that's stretched in one of the dimensions. So after that, as far as how the stretch goes, I kind of thought, well, that would mean it stretches x, but it actually squishes x. You want to know the easiest way to graph the ellipse? I could put it in standard form, but the easiest way is zeros. If x is 0, then what's what? 3. Now, or negative 3, but y is only positive. If y is 0, then it's a little messier. But isn't x squared 9 over 2, which is about 4-ish? Square rooted would be about 2-ish. And so I think about 2. So let's do it. Top half. How'd you do that? Molto bene or not so bene? Bene, bene, molto bene. Okay. How about asymptotes? First, let's get the graph. The function, if you recall, was this. You know 1 over x, the parent graph, or the base graph, I guess you could say, looks like this. It's centered around the origin. What are the transformations that work here? Right 3, up 2. I prefer to redraw my origin than right 3, up 2. This is my new origin, I guess you could say. Now then the shape would still be the same because there was no reflection or anything like that, so it looks like that. Cool. All right. There are 2 asymptotes there. Sorry. Let's do increasing first. Where is it increasing? Never. Okay, remember it goes left to right, do the y's get bigger. Well, if I trace along this curve, left to right, the y's are definitely getting smaller. And the y's are definitely getting smaller. So the answer is it's increasing? Never. Asymptotes. 3 and 2, right? No. Equations of asymptotes are y equals 2 for a horizontal asymptote and x equals 3. Test review real quick. There is a vertical asymptote if a limit statement happens this way. The limit of f as x approaches what, and what does the limit work out to be? There's a vertical asymptote if x is approaching what? A number, okay. And if there's a vertical asymptote, what are the y's values approach? Plus or minus infinity. Isn't that what happens at an asymptote? As you get closer and closer to some number, the y's get big and or negatively big. Horizontal asymptote, if as x approaches what does the limit come out to be? As x approaches a constant, or the limit is a constant? It's really the switch. Look at this horizontal asymptote. What's x doing? Is it going to a constant or is it going to infinity? X is going forever to the right, which means it's going to infinity, or negative infinity, by the way. And what is y going to? It's a constant, okay, or an a, whatever you want to call it. Okay. If the function is increasing, a tangent line drawn at that point is sloping up, so the derivative is positive. We'll talk later about how you can decide if something's increasing by looking at the sign of the derivative. If you were to sum this up in 3 letters, you'd say IVT. True. Okay. first thing you must state for IVT to apply, in other words, for it to pass through all the values between two endpoints, it must be continuous. H is continuous because it's based on f and g. I don't care if you justify why you said H is continuous, but you definitely need to say H is continuous. Okay, you should, if you really wanted to do this well, you would say it's because f and g are continuous. Now you start looking at, all right, well, what is H like at the endpoints? Where does it go from and to? One endpoint is H at 0. Now this you have to kind of follow it through. Here's what H does. It takes G at a point, figures that out, and then puts that into F. So at 0, I'm going to put 0 into G, take that result and put that into F. What's G at 0? 2. And then I put that into F, and F at 2 is -1. Okay? H at the other endpoint, 5. Where does it go to? It's starting at -1. Where does it go to? F at G at 5. What's G at 5? 0, and that then gets put into F, and F of 0 is 3. H went from -1 to 3. Must H pass through 2 along the way? Yeah, that's continuous, and it is. So, H equals 2 is between -1 and 3. So it must pass through. If it were outside, then I guess I would say it doesn't necessarily have to pass through 17. I conclude by IVT, there must be, whichever you prefer, there must be a C in the interval 0 to 5. That must happen in 0 to 5 such that, or where H at that number, whatever that X is, has to equal 2. How'd that go?
How do we know that F and G are continuous?
Did I not write it in?
Right above.
Oh, F and G.
Yes, I actually got to the copy room and I said, oh, I have to do this. That's true. Okay. 23. 23, evaluate the limits. What did you say for the first one? I can imagine two answers. Negative infinity or positive infinity. Which is the appropriate answer? It is negative. Make sure that you don't just boil it down to the variable, but also look at the coefficient and sign in front of it. If you look at negative x squareds over x, that's negative x, and that would go to negative infinity as x gets infinitely large. The next one, what'd you say for that one? It's obviously 0 over 0 upon direct sub. What did you do, and what did you get as an answer? Factored it, canceled out a factor, and what did you get at the end? 4. Okay, factor, cancel. And then last but not least, if the limit as x goes to 2 is 3 over 0, that's rise of 3, run of 0. Think slope. If you rise 3, run none, what kind of slope is that? Vertical, yeah, it's vertical asymptote. It implies, what about the graph? This is infinite, this is undefined, and so there's a vertical asymptote at where? X equals 2. All right, and then the derivative estimation problems. Remember the idea of the derivative is take the slope between 2 points and then get the 2 points as close together. Now that's true in the table also. If I want the slope at 0, then what 2 points should I use? 0 and 2. Show that's an estimate. Show the background of what you're doing before you go to the table. Then go to the table. It would be something like -2 minus 7 over 2, -9/2. Again, when you do slope, it doesn't matter if you do y1 minus y2 or y2 minus y1, as long as you do the same thing at the bottom. Okay? It should always come out the same. Estimate f prime at 2. I would take one of two answers. One answer would be -1, I would find acceptable. The other answer would be 6. Those are the only two answers I would say. So, if you did -1, then it's because you said around 2, I could use the 2 points around it. Now, if you use points on either side, that's the symmetric definition of doing it. It's when you, rather than use the point you want, you use a point on either side. If I did that, then I'd be saying the slope of 2 is like the slope between the points around it, and that then is where you would get 4 minus 7 over 3, or -1. That's an okay answer. Another okay answer is to use the point you want and another point, which would be 2 and another point. What other point should I use? 3. Why not 0? Further away. Okay, the limit idea says you're supposed to take the points as close as you can. And 2 and 3 are 1 unit away. 2 and 0 are 2 units away. Why would you choose 2 and 0? They're further away. So choose 3 and 2. If you did a one-sided derivative approach. 4 minus -2 over 1 is 6. Either of those answers would be satisfactory with appropriate work to justify. F prime at 3. Again, you have a choice between, should I go on either side? If you use the symmetric approach, you could go f at 5 minus f at 2 over 5 minus 2. So I would take 5 over 3. That's symmetric, one on each side. If you use the one-sided approach, you'd use 3 and what point? 2 or 5? 2, because it's closer. And obviously then it would come out the same. Or 2 and 3, which is equal to 6. Okay, and then f prime at 4. 4 doesn't actually even happen in the table, so what's the only definition I can use? Symmetric. I have to use the symmetric. I have to use a point on either side. And so that's f at 5 minus f at 3. 3 minus 4 over 2. Okay. I think that's all I added on to or replaced. Other questions on set 25? Shout them out. Yes. 20.
That was my question.
20. Okay. 20. If you have other questions, be free to shout them out, and I do mean shout them out because I am as deaf as it comes. 20. The old identities. I didn't replace this, did I? No. Okay. So, I went back and forth on whether to assign this or not, but there are a few identities that you need to have. Sine of 2x is one of them. You'll need sine of 2x. This one, cosecant of -x, that's definitely not a big idea, at least not until we get to even or odd. So if you didn't remember that, that's okay. But, that said, here we go. In terms of how I teach identities when I teach pre-calculus is I take one side, usually the more complicated side because there's more to do, and manipulate it one step at a time until it looks like the other. I never make more than one change at a time so as not to lose the person reading it. So what's one thing I can do to this side? Let's start here. What can I do that? 2 sine x cosine x. If by identity you replace that, keeping the left side, or everything else the same, the right side I'm not going to even touch, then that makes my life a little more simple. Boom. I now have 1 over sine of x cosecant of -x. I'm already starting to get somewhere. Look at where I'm headed. I need a negative. I need a square. So what do you reckon next? Sine in the denominator. What can I call that? cosecant in the numerator, weak. At that point, I've danced around the even odd thing as much as I can, and you need to actually deal with the problem. The idea is when you put in a positive x or negative x, what happens? On cosine, if you look at cosine, wouldn't you say that the cosine of a positive x, or the y value I get for this point, is exactly the same as the cosine I get for the same x on the negative side? That's an even function. For sine, however, if I look at sine of x versus negative x, this x here is going to be a totally different y value here. The number will be the same, 0.2 or whatever, but the sign would be different. Now that implies that when you put in a negative into the sign, you actually get the opposite y value of the positive side. Notice I never said you pull the negative out front, which is just nonsense. That's not true. Okay? There's symmetry across the order. So, because sine and cosecant are so closely related, this will behave exactly the same way. The cosecant of negative x would give you the opposite of when you take the cosecant of a normal x. And then obviously you run it in for the touchdown, and you spike your pencil. Like that. And then you do your touchdown dance. Hey, Broncos played tonight. Hey. Okay. Does that make sense? I'll come back to you now. Oh, yeah, that then leads you off the program. That makes sense though, both seats. I don't know why they didn't do that. That would make more sense to me. All right. Any other questions on set 45? Ow, that hurt. Or any other questions? Do I keep doing it? That's the All right. Let me know if you have questions. I will be happy to help.
I don't know.